Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is a very interesting topic, principle of Vinylogy. I believe that majority of you know this, but you are a little confused that is it called Vinylogy and what is the importance of this we shall learn. Mainly its application in organic reaction, and not only that, during this discussion we shall learn the mechanism associated with this process, many example and one MCQ. So before going to the details, the MCQ. What is the major product of this reaction? So 4 options are provided. I request you student, please pause the video, try by yourself, and whatever answer you get, please write in the comment box along with few words supporting your answer. And don't worry, after some time we'll get the right answer or with explanation. But before that, the main discussion, that is Vinylogy. So Vinylogy is the transition of electronic effect through a conjugated organic bonding system. Okay, for example, a carboxylic acid with a carbon double bond means this part, or vinyl moiety, or actually vinylene group it is. So between the carbonyl group and the hydroxyl group is referred as vinylogous carboxylic acid. But before going to that, just look at ketone, simple carbonyl, because ester is also a carbonyl. This is acetone, I guess, means if this R is CH3, this is acetone. Now if you compare this ketone versus this, I am focusing on these two parts, student, encircle part. What is the difference? Only difference is this carbon-carbon double bond. Okay, and for that some property changes, some property remains, and that is the today's topic of discussion. Because of this double bond, which property remains and why, and how this affects, or how this you can observe in organic synthesis, today we shall learn. So as our discussion about vinylogous carboxylic acid, what is this carboxylic acid? So first one is a simple carboxylic acid. If R equal to methyl, you can consider this is acetic acid. Then we know this acetic acid shows its acidity, means it undergo proton deprotonation, means deprotonation. Not only that, if you take this is as a formic acid, it's the simplest acid, let's come to the simplest, then this proton elimination even further easier. Its pKa in between 3 to 4. It's significantly strong acid like formic acid. We know the minimum member, first member of this carboxylic acid series. What is the vinylogous counterpart of this carboxylic acid is, or formic acid, is this one. Okay, what is the difference? In between this carbonyl and oxygen there is one double bond, or more specifically if I say, it is actually a carbon-carbon double bond. If you look this molecule little different angle, you can say that, sir, this is an enol. It's true that this is an enol. Fine. Not only that, enol, it can act as an acid, because in between these one vinyl group is there. So this part you can consider as vinylogous carboxylic acid, and it also shows acidity like the formic acid derivative. In this case R is also equal to H, and in this case pKa is near about 5 to 6. Property is slightly different, but acidity shows. But if you compare this with a traditional enol, just focus on this part. Traditional enol, if I say, means this one, its acidity or pKa is near about 12. Okay, and if you can compare this thing with your a very known system, that is phenol, near about 10 its pKa. So from that you can understand that this acid is slightly more acidic. It is slightly more acidic because it is vinylogous carboxylic acid. It has the property of carboxylic acid. Fine. So I know you will not be that much satisfied that, sir, what example you are talking is not that much well familiar. By the way, there is one molecule you are extremely familiar and have already discussed a dedicated lecture, that is vitamin C or ascorbic acid. I know you people are extremely familiar with this vitamin because during this COVID time it was prescribed not for patients who are also normal healthy people. So suggested that please take some amount of vitamin C in the form of food or in form of pills. So this vitamin C or ascorbic acid is also a vinylogous carboxylic acid. Which part? Just look at this part and compare this with the previous one. So this part is vinylogous carboxylic acid. Why? Because here a carbon-carbon double bond is there. Okay, so that's why this is called. And if you look at the deprotonation, means removal of H plus, it produces, this is the O minus. Here it has also a resonance, means this lone pair of electron can come here, it can come here, it can open. So that's why this comes. And if you look at the pKa 4.10, you will be surprised. Previously pKa was 5 to 6, here 4.10. Now a question may come that, sir, this is actually an enol. This part, how it could be very strong acid? This is because it's vinylogous carboxylic acid. Okay, so that's the proof of this statement that vinylogous carboxylic acid exists. Now let's go to another question. Is there any system phenyl groups? Generally, because when we say anything about this enol, then a question comes that there is molecule means phenol. So is there such kind of thing happens in case of aromatic or phenyl groups? Yes, true, it happens, but we shall come after some time. Before going to that, let's learn about this vinylogous system. Just some time before we told vinylogous carboxylic acid. Now if you look at this molecule, in this case the question is which CH3 proton is relatively more acidic. What I am talking about actually, this proton A and these protons B. So which is relatively more acidic? Now obviously A is more acidic. Question why? Because this is also a ketomethyl group, and if you look at this side is also vinylogous ketomethyl group. So when you write anything, this term you write this vinylogous, this is vinylogous ketomethyl group, but this is more acidic. Why? Because these methyl means these methyl, after this deprotonation, what it will produce? It will produce a carbon ion here, means this will be CH2, this is minus. Now this carbon ion is resonance stabilized, I is true. In this case, the second one case also, the carbon ion is resonance stabilized, this is the CH2 minus. But this carbon ion faces two type of effect. One is minus I, another is minus R, both significantly, because it is adjust to this carbonyl group directly. Okay, so both minus I and minus R operates from this carbonyl group. But if you look at this molecule, this CH2, this part, it faces the minus R effect, but it doesn't face the minus I effect. Why? Because carbon chain 1, 2, 3, 4 carbon apart, or very weak minus I effect. So from that point of view, you can say that A is more acidic compared to B. Now in this context, I request you to recall the difference between aldol reaction and Michael reaction, and by the way, I have already discussed dedicated lecture on this topic. And another interesting question, what happens if this carbonyl, what I have presented here, is treated with sodium deuteroxide in D2O, and why it will happen? I am giving you this home task. If possible, please do this and write the answer in the comment box. Not only that, one MCQ which I have already uploaded, that is about this deuterium exchange. So if you keep this compound, I am giving the hints, in sodium deuteroxide in deuterium for longer time, it exchanges deuterium. So which portion? In this case there are three types of proton, four times, one proton here, one proton here, one proton here, and one proton here. So 1, 2, 3, 4 types of protons. So which proton is expected to be replaced? Please try by yourself and write your answer in the comment box. Now let's come to real example for the Claisen ester condensation. By the way, students have already uploaded many dedicated lecture on Claisen ester condensation, so I shall not go to the mechanism. I shall briefly explain what happens. If you look at ester, then this ester does Claisen ester condensation with diethyl oxalate ester. Why these oxalate esters are selected? See, in this case, these oxalate ester have two carbonyl together, or you can consider this is 1,2 dicarbonyl compound. That's why these carbonyl groups are extremely electron deficient. So they are very good electrophile, strong electrophile. So that's why, and in this case, if you look at this oxalyl ester, this group has no alpha hydrogen. So if it has no alpha hydrogen, then it cannot produce the enolate and participate directly, whereas if you, and it is more reactive. So if you take this mixture of this, this is ethyl acetate which has alpha hydrogen and 2 alpha hydrogen, so it can efficiently react and ultimately produce this 1,3 dicarbonyl compound, just 1 and 3 relatively. This is the product, and by the way, it has also a name. This 1,3 dicarbonyl compound is also named as active methylene compound. Okay, in chemistry, I guess you have heard this word many times. What is active methylene compound? Such 1,3 dicarbonyl compounds are called as active methylene compound, and they have a unique property because these two protons are significantly acidic. Okay, so after workup we get this product. Fine. So similarly, this thing, and how this reaction happen, these reactions start by generation of carbon ion here. Okay, so this is actually a enolate generation from ester, which act as nucleophile, attacks here, it opens up, come back, and ultimately it leaves, and through then steps are there, it produces this 1,3 dicarbonyl compound. Now similar properties observed if you take this alpha beta unsaturated ester. This is alpha carbon, this is beta carbon, and in this case what happened, this gamma carbon undergo deprotonation and produces this enolate, and these enolate act as nucleophile here and follows the same pathway and ultimately produces 1, 2, 3, 4, 5, so 1,5 dicarbonyl compound. Now I request you student, please recall the application. As I told, one is dicarbonyl compound, and another one I am giving you. What is the application of 1,5 dicarbonyl compound? This is used for 6-member heterocyclic compound. I have already discussed many dedicated lectures on this, you may visit, and one of the most famous 6-member heterocyclic compound is pyridine. I guess many of you have heard or seen or learned about this compound. So this is prepared. So if you check the carbon number 1, 2, 3, 4, 5, and 1 is nitrogen, 6-member heterocyclic compound. Now not only that, just look at another example. This is alpha, beta, gamma, delta, epsilon. Okay, so this also does the same thing. What it does, it produces this 2- or carbon ion, and this carbon ion act as nucleophile here and it produces this compound. Okay, and as an intermediate, initially it means in presence of base, initially it produces a conjugated thing, means this is, you may consider it's an enolate. So after workup, or more specifically say if I acidic workup, ultimately this is produced. So see how the property is extended, means from alpha beta unsaturated means 1 double bond, similar property. In case of 2 double bonds, then also similar property, and that is the uniqueness of this Vinylogous system. Means they retains the property or electronic properties transmitted through carbon-carbon double bond. See, increasing of carbon-carbon double bond property still remains. Otherwise, for example, if you take this is also a similar compound here, means 1 alpha, beta, gamma, delta and epsilon. Then if you do the same thing reaction with this, where the reaction is expected to happen? Here, carbon ion will generate from here and it will participate in the similar reaction. So from this thing you can understand what is the clear difference between the Vinylogous system versus normal system or saturated version. Now, so not only that, if you react this alpha beta unsaturated carbonyl compound with Grignard reagent, there is a competition because Grignard reagent is carbon ion negative or delta minus, whatever you can consider. So this is actually a nucleophile. Okay, so this is actually a nucleophile, and these nucleophile have two choice. One is 1,4 addition and one is 1,2 addition. By the way, what do I mean by 1,2 versus 1,4? This is 1,2, this is 1,4. So means nucleophile if attacks here, then that is called 1,4 addition. If the nucleophile attacks here, then that is called 1,2 addition. By the way, I have already discussed a dedicated lecture on abnormal reaction, which actually nothing is abnormal, everything is normal based on chemistry point of view, but they are little different compared to traditional reaction. That's why people call it abnormal reaction. Okay, so Grignard reagent and alpha beta unsaturated carbonyl compounds, I request you please visit for better understanding. Now let's come to another example, Vinylogous ester hydrolysis. So this molecule is called Vinylogous ester. Now you can say that, sir, why are you saying Vinylogous ester? Just try to recall the structure of Vinylogous acid. This is Vinylogous acid. So what ester you can expect? That this part carbonyl, this OR, this is Vinylogous ester. So if you look at this CO2ET, it is nothing but COOET. Just this way try to understand that COOET. Okay, so this is, now this is CO, then one vinyl, then OET, similar OR. So this is Vinylogous ester, and how it can undergo hydrolysis. So it reacts in presence of water and alkali, and it produces ultimately this compound, obviously first alkali, second H3O plus. Okay, this, how this reaction happens? First, this OH minus is produced. Why? Because alkali, I told, means in the medium there is OH minus which act as nucleophile. It attacks here. It is the alpha, this is the beta of carbonyl. You know, beta position of carbonyl is significantly electrophilic, so it is electrophilic. It attacks, it opens up, it opens, it produces this one. Okay, enolate type derivative. Second, it come back here, it comes here, and this leaves. And ultimately what it produces? Obviously this. But student, remember, this is an still alkaline medium, and this is actually an enol. So we know that enol can undergo tautomerism, or better to say keto-enol tautomerism, and ultimately it can convert into this compound. Okay, so this is carbonyl, and by the way, if you look at this compound, there is also one proton. Now this proton is in between three carbonyl, two carbonyl from here, means diethyl malonate, and one carbonyl is from the aldehyde. So just consider, if you compare the parent diethyl malonate CO2ET versus CO2ET, we know that diethyl malonate proton is significantly acidic, pK near about 11-12, like that, I am not exactly sure. So if you put another carbonyl compound, what will be the pK? This is significantly acidic. So you can consider this is very acidic with respect to carbon hydrogen bond. Okay, very acidic, or stronger relatively acidic. So in alkaline medium you will not get this compound. For that you need to do workup. Workup means acidic workup. I guess you have understood why I have written H3O plus here. Okay, so this is the product. So this way Vinylogous ester hydrolysis happen. And by the way, student, these reactions are reversible, it's true. So I haven't shown because of complication. Now in this case I request you, please recall the mechanism of aromatic nucleophilic substitution. This aromatic nucleophilic substitution with acyl nucleophilic substitution. So I shall come after some time. So first learn about this acyl nucleophilic substitution. Means, for example, this is acid chloride, it reacts with pyridine and ultimately it produces ester, and for that purpose triethylamine is used as, pyridine is used as base, and ultimately it produces this pyridinium salt. So by the way, I have already discussed a dedicated lecture on this acyl nucleophilic substitution mechanism and intermediate trapping. Please visit for understanding, because mechanism understanding is essential for organic chemistry. Now what happens here? If you look at the mechanism, this alcohol first attacks here, and it's open up, it comes back, and this means first it open up, so I will not say leaves. So it produces this sp3 or tetrahedral intermediate, and after this reaction this oxygen got a formal positive charge OH, And what does this pyridine does? It acts as a base and it abstracts this proton. So in this way it neutralized. Later on it comes back and it leaves. So ultimately it produces this. This is the ester. So just try to recall the first one, similar type of mechanism, but in between there is one vinyl, nothing else, but chemical property is similar. Not only that, there is a term called phenylogy. Phenylogy means you can consider the phenyl analog of vinyl group. I told sometime before, I shall explain. The insertion of ortho and paraphenylene, that is in benzene ring in 1,2 or 1,4 orientation, also result in some similarities in relatively called phenylogy. Although this effect is generally weaker, as conjugation through the aryl ring requires consideration of resonance from the intermediate which aromaticities disrupt. I shall explain. If you look at, this is actually a trihydroxy 1, 2 and 3. So this 1, 2 and 3, if you take and treat with alkali, what will happen? One with OMe will leave, this paraverse one. Okay, this is, and if you look at little closely, student, just see here, just look at the part under this green part, double bond 1, so double bond 1 and this is double bond 2. Okay, so this is also you can consider vinylogous system having 2 carbon-carbon double bond. But what is the difference? Because previously we are talking about just this isolated double bonded vinylogous system, but in this case there is another thing. So this is actually a ring and this ring is aromatic, means it is extremely stable, that is somehow reduces the reactivity. But in this case what happens? This hydrolysis happen and ultimately it produces this acid. And by the way, not only that, if instead of that, if you take compound, like for example, if you take this chlorine, this is orthonitro, this, and if you treat this with alkali, I guess you all are almost familiar with this. What is the product? Through aromatic nucleophilic substitution, this produces orthonitrophenol. If you look at this system little carefully, this part is also a vinyl system type. Why I am saying only one double bond, student? Vinylogous. So in this way you can compare, means this aromatic nucleophilic substitution in ortho and para position is also similar like vinylogous system. So same concept could be utilized to explain both of the phenomena. So how this reaction happens? Because first it attacks here, produces this carbon ion, then it undergo resonance, means it can come here, it can come here. So ultimately negative charge is here, it can come, it can open here. It produces this intermediate, again negative charge will come, it come here, it will come here. So in this way ultimately reaction will happen. Sorry, I made a mistake. It will come here first. So it will come here. Second, then the negative charge will be pushed and negative charge will come here, later on here, and this carbon OMe leaves. So this is the overall strategy. But if you look at this intermediate 1, intermediate 2, intermediate 3, 4 and 5, in this case aromaticity is lost. Okay, aromaticity is lost means the ring was aromatic previously, but in this case aromaticity is lost, and we know aromaticity is a significantly higher stabilization energy, and in order to get the reaction, means para-hydroxy and OMe3, these we need to sacrifice a huge amount of stabilization. Although you can say that, sir, there is aromaticity gain at the end, but intermediates are associated with the loss of aromaticity. So you can consider that energy of activation of such kind of process is significantly higher. So this is the difference between phenylogy, means phenylogy versus vinylology. Okay, so please try to remember this thing. Now similarly other groups behave similarly due to vinylology. Is this is the acid, this is the vinylogous acid. I have explained this thing. This is the amide or acid amide, this is vinylogous amide, vinyl group. This is ester, this is vinylogous ester. This is acid chloride, this is vinylogous acid chloride, means similar property you can expect. And this sometime we say aromatic nucleophilic substitution, aromatic nucleophilic substitution type or acyl nucleophilic substitution type. So all are similar electronic property, but based on changing the system, the name got changed. Now let's come to other examples like nitrile based vinylogous system. Student, this is similar like Claisen, because nitrile C triple bond N. Previously in case of this Ester, Claisen ester condensation, there is a double bond, triple bond, so similar. So this is simple acetonitrile. Similar reaction means carbon ion will be generated here, this, and these will attack here and ultimately do the same. This is also 1,3-dicarbonyl type compound, and by the way, this is relatively more acidic than the Claisen analog, because cyanide is more withdrawing compared to simple ester. Now similar thing is happened here, carbon ion is generated, it does the same thing. Not only that, here also carbon ion generates and it also does the same thing, and ultimately it produces this compound. So this is the overall understanding. Now a question may come in your mind that, sir, why always this bond, means this part is gone, means it's a completely conjugated system, why this part is like that? Just try to remember, student, the intermediate was enolate type. So in after workup, means acidic workup, this enolate will be converted into keto. So that's why this is gone. Okay, so but by the way, remember this is significantly acidic, because after deprotonation of this proton, the system becomes conjugated. Now let's come to an additional interesting point, that is Michael addition reaction. Michael addition reaction, student, always happens on this carbon, or more specifically if I say this beta carbon or others. So first Michael addition happened, and in this case what is the nucleophile? Nucleophile produced from this diethyl malonate or DEM. Why? Because it has a proton, and this proton is significantly acidic, it's active methylene compound. Okay, so in presence of base, this proton is abstracted, and what it does, it produces a carbon ion here. Okay, and this carbon ion is act as a nucleophile, means it goes and it attacks here, it opens up. Okay, and after that it comes back. Okay, let me draw the intermediate, I guess that will be better. So this is the pH, this is the CO2 ET, this is CO2 ET. Here 2 carbons, 1 2. Now so this is O minus, okay, and this is the pH. So and second, it will undergo, this is enolate type, so ketoenol tautomerism means proton abstraction, and ketoenol tautomerism ultimately will result in this one. Now you may ask one question, that, sir, this looks like 1,4 addition type. So 1,2 also possible? Yes, student, there is a competition between 1,2 versus 1,4, but remember one word, nature of the nucleophile means negative charge density, how much, what is the bulkness of this nucleophile, this is the nucleophile. And not only that, this phenyl and these phenyls means what are the substituent at this position attached to directly ketone or beta position. All these things determines whether 1,4 will dominate or 1,2 will dominate, and this Grignard reagent and alpha beta unsaturated carbonyl, that video explains a lot. So that's why I told please read. Now similarly, in presence of base, this DEM will be converted into this carbon ion, and in this case the property gets shifted here. So you can see the same type of reaction here. Okay, and by the way, a question may come that, sir, intermediate is an enolate. Now question, why the double bond is here? It could have been come here. What do I mean by the statement? Let me draw. Just this is CO2 ET twice, this is carbon, this is pH. I am talking about this double bond, this CO2 ET. See the double bond from these alpha beta, this is gamma delta. So from alpha beta it is shifted to this gamma delta. Why not this? Student, remember one thing, that this part is relatively more stable. Okay, you can say that, sir, phenyl group is in conjugation with double bond. It's true, but it is not that much stabilizing compared to these alpha beta unsaturated carbonyl derivative. and that's why double bond remains here. Okay, so in conclusion, what you have learned today, that using the principle of this Vinylogy, we can explain many properties of conjugated system. I repeat, conjugated system. Vinylogous system continuous chemical behavior of diphenyl functional group. For example, this acetonitrile and this alpha beta unsaturated derivative. Similar, next methyl group goes. Increase in the number of carbon-carbon double bond, the effect get less prominent. As I told, in case of acidity of these two carbonyls directly ketocarbonyl or vinylogous ketocarbonyl, because the position changes, means distance, both minus I minus R initially, later on only minus R. For phenyl group, such kind of properties observed with aromatic nucleophilic substitution. So similar way we can explain the phenomenon. And finally, in Phenylogy, the activity is relatively less due to disruption of aromaticity. As I told, 5 intermediates which is involved with the destruction of aromatic stabilization. So let's come back to our MCQ. What is the major product of this reaction? Student, this is actually nothing but triethyl orthoformate. I have already discussed about orthoester, so please visit. This is a very interesting group of molecule. So this is, you can consider that acetal, means in this case I will say the acetal version, because is of ester, means this HCOOOET. So this is formate ester. This formate ester's carbonyl group is acetal formation with ethanol. So it's like that. So in chemistry, this is, in chemistry sense, this is the reaction of this active methylene compound or DAME with this formate. Now what is the nature of this DAME? In presence of base, it undergo deprotonation, produces this carbon ion. So what this carbon ion will do? Let's learn this mechanism stepwise. So first this carbon ion generation, and second this carbon ion is actually resonance stabilized, and this resonance stabilization is possible with this 2 DAME, an equivalent canonical form, means this negative charge is completely delocalized, but nucleophilicity is observed from the carbon center, means here, because of the softness. So this act as a nucleophile. So what can happen, that there is a lone pair of electron, so under this reaction condition it can push and one can go, so it will produce this. What is this, student? This is one hydrogen. So you can consider this as cationic ester or protonated ester derivative, because this is the ester carbonyl and it attached to an alkyl group, so that's why positive charge, and because of this positive charge means it is more electrophilic or electron deficient. So reaction can happen smoothly. And another thing, if you look at, this is not that much bulky too, because formate hydrogen is there. So what happened in this case? These negative charge will attack here. Okay, so it will attack here and it will open, and ultimately this is the addition product. Now just look at this part, that is beta hydroxycarbonyl derivative. Like in aldol condensation, this type of reaction happened. So in this case, what it will do, in this case ethanol molecule will be eliminated from the reaction medium, and ultimately what it will produce, it will produce this vinylogous ester. Just I have discussed this thing in between, also hydrolysis. So this is the product. So in this case, what is the product? The product is option B. Okay, so now the question is, if this question appear in your exam less than 30 seconds, how can you solve this question? Point number 1, you need to know one statement, that this ethyl orthoformate is equivalent to ethyl formate. Okay, so it's may consider that saturation is not, but chemical property is same, and base and active methylene compound means carbon ion generation and nucleophilic addition. These two part enough, and I request you student, please try to draw the intermediate. So if you do that, so what it will go at the beginning, this 2 OET gone. What is left? Only, means this is equivalent to this, so addition will happen here. So ultimately after elimination, means double bond formation, in all structure there are double bond, you can see. So only 1 OET will be left. So in which case only 1 OET is left? Only option B and D. Point number 1. Second thing, in case of option D, it is shown that the decarboxylation happened. That means there is one less carbon, means ester group. Why? And how this is possible? This decarboxylation of beta-keto acid only possible by hydrolysis and decarboxylation. But did I provide any hydrolysis, any water I have mentioned? No. So if no hydrolysis is mentioned, how decarboxylation will occur? So this is not possible. So this thing you need to think quickly, that first, okay, this is equivalent to and format ester, second it's nucleophile. So these are two options possible, and decarboxylation is not possible here because no water given. So this option B is the right answer. Okay, so this is the end of the discussion. I believe this video may be useful for you. If it is, please help this channel to grow, and you may visit my another channel where I upload global warming and climate change related videos. So thank you again. Stay happy, stay blessed.